Okay, this is quiz 1 of the AP review. It's multiple choice. It's video 2, problems 11 to 20. So the first quiz of the AP review, multiple choice video, problems 11 to 20. The manager of a public swimming pool wants to compare the effectiveness of two laundry detergents, detergent A and detergent B, in cleaning the towels that are used daily. As each dirty towel is turned in, it is placed into the only washing machine on the premises. When the washing machine contains 20 towels, the manager flips a coin to determine whether detergent A or detergent B will be used for that load. So what we have here is we have a random assignment. We flip a coin, and based on flipping a coin, we either get detergent A or we get detergent B. The cleanliness of the load of the towels is rated on a scale of 1 to 10. So afterwards, we compare cleanliness, how clean it is. All right. By a person who does not know which detergent was used, in other words, was blinded. The manager continues this experiment for many days. And by the way, it is an experiment. Which of the following best describes the manager's study? Well, I randomly assigned the detergent. There was no blocking. This is a completely randomized design. If it were a block design, I could block it based on how dirty the towel was, or I could block it based on the color of the towel or things like this. But there was no separation. I just said, hey, I loaded up 20 towels, flipped a coin, randomly assigned the detergent. There we go. All right, so this is a completely randomized design. Number 12, in a design of a survey, which of the following best explains how to minimize response bias? Okay, so increase sample size. First off, sample size has nothing to do with bias. Sample size changing sample size changes variability or sampling error, but has nothing to do with bias. So those two, sample size has nothing to do with it. Randomly select a sample. You need to do that regardless. That has nothing to do with response bias. It is a good thing to do. We should be doing this. But response bias specifically is that the question is worded in such a way or presented in such a way or is a sensitive question. Regardless how you say it, it's worded weird, phrased in an odd way, presented in an odd way, or it's a sensitive subject so that the person is not likely to give the accurate response. They're likely to either intentionally or unintentionally give a lie. So to fix the problem, we need to carefully word the question, and it helps to field test it to make sure that it's not a sensitive topic. All right. So once again, poorly worded questions are response bias. Poorly presented questions are response bias, meaning if I act angry when I present it, that can be response bias. Or the other thing is if it's a sensitive question. Number 13, for a sample of 42 rabbits, the mean weight is 5 pounds. This is probably important for you too. And the standard deviation is 3 pounds. So we have a mean equal to 5 and a standard deviation equal to 3. Which of the following is most likely true about the weights for the rabbits in the sample? This is important. This says weights of the rabbits. It doesn't say mean weights. Had it said mean weights, if it had said mean weights, we go, hey, n equals 40 greater than 30, normal by central limit theorem. But they did not include the phrase mean weights. They just said, what are the weights? So in other words, what's the distribution of the sample? Well, let's just make it easy on ourselves initially and begin and act like this is a normal distribution. Well, if it's a normal distribution, we're going to have 1, 2, 3 above the center and 1, 2, 3 below the center. So I'm going to try and fit a curve to this. That's not perfect, but it's good enough. Well, my standard deviation is 3, then that means I could have 8, 11, big fat bunny at 14, 2, and then here I get to -1. Well, I can't have any rabbit less than 0. So this is what my shape is. So basically this part doesn't even exist because I can't have a bunny less than 0. So the distribution of weights is approximately normal because the sample size is 42. No, the distribution of the mean weights is, but not the weights. The distribution of the weights is approximately normal because the standard deviation, now that has nothing to do with anything. They made that up. The distribution of the weights is skewed to the right because the least possible value is within 2 standard deviations. And that's what we showed here, right between 2 standard deviations. Or if you wanted to, you could check it out. Z equals X minus mu over sigma. Well, the least possible value would be 0 minus a mean weight of 5 divided by 3. And 0 minus 5 is -5, which means all of a sudden -5, excuse me, clear. All right, -5 divided by 3. So we end up with -1.6 standard deviations. It's like, no, that's not possible. We can't have anything because we have to have 2 to 3 standard deviations below. We don't have the 2 or 3 standard deviations below. So C for 13 is our best answer because we can't have negative bunny weights and we're missing this part of the curve. We have to have 0, 1, 2, 3 above and -1, -2, -3. We have to have 3 below and we don't have those over here. We don't have the -2 and the -3. All right, number 14. First off, number 14, they did not count this on the test and they actually don't provide an answer because they messed up when they worded the question. But we are going to talk about it a little bit, even though we can't give the exact answer, because I think I know what they were going for. When conducting a large sample test, the null hypothesis is P equals P naught for a single proportion. All right, so we have P hat minus P naught over P naught Q naught N. Which of the following explains the justification for the denominator in the test statistic? So here's what I think they were going for. Here we have in the denominator P naught Q naught over N, whereas if we were looking at a confidence interval, our standard error would be P hat Q hat over N. Well, why did we do that? Well, there's a couple reasons, and I'm going to talk about both of them. First off, HO. P naught equals some value. We believe this to be true, and because we believe it to be true until we find evidence to the alternative, we use it. Since we believe the P naught is correct, we use it. Over here, we don't have a P naught. We're trying to estimate P naught, and we use our sample to estimate it. But here, because we believe the null to be true, we use this until we find enough evidence against it. We don't use P hat for this test. We don't use P hat for this test because we believe P naught is the actual value. It's because we believe it's the actual value that we use it. In other words, because we included it in the null. Here, we don't have a P naught. We're trying to estimate it, and we use our sample proportion to do so. But not, regardless, number 14 does not have does not have a correct answer. All right. And the best answer, I think, would have been D, but because that is the standard deviation of P naught is known when the null is true. If this is true, we know it to be P naught. I think that is the best answer, but it's a poorly worded question. They said skip it. We don't count it, so we're not going to talk about it. We're not going to worry about that one. All right, number 15. And by the way, when you took your quiz, number 14 had no answer. There was no correct answer, no wrong answer, because College Board didn't count it, so we're not counting it either. All right, number 15. A polling firm is interested in surveying a representative sample of registered voters in the United States. The firm has automated its sampling so that random phone numbers within the United States are called. In other words, it's going to just sit there and take a random number generator and dial all sorts of random numbers. Okay, each time a number is called, the procedure is followed below. If there's no response or if an answering machine is reached, another number is automatically called. If a person answers, a survey worker verifies that the person is at least 18 years of age. If not, they hang up. If the person is not at least 18 years of age, no response is recorded and another number is called. So if someone who's a minor answers the phone, oh, you're a minor, they hang up and they call another number. If the person is at least 18 years of age, that person is surveyed. Some people claim the procedure being used does not permit the results to be extended to all registered voters. Which of the following is not a legitimate concern about the procedure? All right, so we're going to have concerns and not concerns. Registered voters with children under the age of 18 may be underrepresented. Well, there was a time that I had 5 children under the age of 18. If any one of them answered the phone, myself and my wife would not be represented. That's a concern because I'm a registered voter. My wife is a registered voter. So that's a concern. Registered voters with unlisted telephone numbers may be underrepresented. A listed telephone and unlisted means I can go to a book and pull up our phone numbers. And if I have an unlisted phone number, you can't look me up to call me. Well, that sounds like that's a problem, except for the fact that they have a random number dialer and they're randomly dialing all numbers, and it wouldn't matter whether I'm listed or not listed because they're randomly using a random number generator to dial. So I don't think this is a concern, but we'll continue to read on. Registered voters who have more than one telephone may be overrepresented. Well, as it turns out, there was a time when I had multiple phones because of my small business, and consequently, you could have called me on each number. As a result, I could have answered the poll multiple times. And since it's me answering the poll multiple times, I would be overrepresented. That's a concern. Registered voters who live in households consisting of more than one voter may be underrepresented. Well, now we only have one phone, or we're going to pretend that we have only one phone. Well, if my adult children were living here, that means I'd have 4 adult children, myself, my wife, and my father-in-law all living here. So that would be, and they're not, but if they all were, that would be 7 people. So that'd be 7 registered voters, but when it calls, it only surveys the one person who answered the phone. So yeah, that's a concern because the other voters would not be represented. Finally, people who are not registered to vote may bias the sample results. Well, if I were not registered to vote and it called me and I answered the poll, then I would be biasing it, so that's a concern. So the only one that's not a concern is B, number 18. So number 15 is B, and it's not a concern because it's going to dial, it's going to just go, the random number generator generated the number 2, then it generated the number 1, then the number 0. See, I got 210 in there, and then it generated the other numbers and dialed whoever it dialed. Okay. A complex electronic device contains 3 components, A, B, and C. The probabilities of failure for each component in any one year are 0.01, 0.03, and 0.04. If any one component fails, the device will fail. So if A fails, the device fails. If B fails, the device fails. If C fails, the device fails. If A and B fail, it fails. So any combination of one or more failing, it fails. All right. If the components fail independently of one another. And the reason they tell us independent is because I need to know if I can multiply. If I can't solve this problem. What is the probability that the device will not fail? In other words, they want it to work. Well, I have three components, A, B, and C. I need this one to work, this one to work, and this one to work. All three must work for the device to work. Well, what's the probability that A works? Well, A works is 1 minus 0.01, which is 0.99. The probability that B works is 1 minus 0.03, which is 0.97. C works is 1 minus 0.04, which is 0.96. And like I said, they said they were independent, so I could multiply them. And by the way, if I showed my work like this, that would give me full credit on an FRQ if that were to occur. So 0.99 times 0.97 times 0.96. And I end up getting 0.29218. So my closest answer to this is 16 is D. Number 17, a large sample 98% confidence interval for the proportion of hotel reservations that are canceled on the intended arrival day is 0.048 to 0.112. What is the point estimate for the proportion? So what they're asking me for is the point estimate of the proportion. So they're asking me for p hat that are canceled on the intended arrival day from which the interval was constructed. Well, p hat 0.048, p hat is going to be exactly in the middle of that interval. So what I can do is, since it's exactly in the middle, and it always will be, since it's exactly in the middle, I can go ahead and do the midpoint formula, which is 0.048 plus 0.112 divided by 2. In other words, we're just taking the average, because the midpoint is just the average of the 2 points. So 0.048 plus 0.112 divided by 2, and I end up getting p hat equals 0.08. Now, had they asked me what the margin of error is, I could have taken 0.112 minus 0.08, and my margin of error is 0.032. So basically, p hat plus or minus the margin of error, 0.08 plus or minus 0.032. And if I should take the 0.08 and subtract 0.032, sure enough, I get 0.048 as well. Regardless, they asked for the midpoint. They asked for the p hat, which is C, 17 is C. Number 18. When using a one sample T procedure to construct a confidence interval for the mean of a finite population, a condition is that the population size be at least 10 times the sample size. And this is when we always go n divided by 0.10. All right, and that's how we do the 10 times. The reason for this condition is why? Well, I want to remind you of that. It's when I have that giant pile of M&Ms, all right, massive, huge, gorgeous pile of M&Ms. If I take one away and it happens to be a red one, the percentages technically change, but they change by such a small amount that no one cares. And that's the same thing here. We want to make sure that even though we're doing it without replacement, that it doesn't have a big impact, a very small impact. So sample size is large enough. That means in this case, n would have to be greater than or equal to 30 for normal by central limit theorem. The central limit theorem is applicable. Once again, n greater than or equal to 30. C has nothing to do with that. The degree of dependence among observations is negligible. Once again, when I take one away, it doesn't have a massive impact. Yes, technically it's dependent, but not substantially so. All right. So the answer to 18 is D. We want to make sure that we're not impacting it substantially. Yeah, when I ate that M&M, the percentages changed, but it changed by such a small amount, no one cared. So as long as we're less than 10%, no one cares. "19, a nonprofit organization plans to hold a raffle to raise funds for its operations. A total of 1,000 raffle tickets will be sold for $1 each." Well, if they're selling 1,000 raffle tickets at $1 each, they're going to sell $1,000 worth of tickets. One ticket will be selected at random and its owner will receive $50. So if we take away $50, we have $950 of profit. Okay. The expected value for the net gain for each ticket is negative 0.95. What is the meaning of the expected value in this context? And what it means is the owner on averages loses 95 cents per ticket, because this is all profit. So this comes away from the owner. 950 divided by 1,000 is 0.95. This is what is kept, is paid. This is what the fundraiser keeps, and the winner gets 50 over 1,000, or 5%. All right. So basically, they're losing every time you buy a raffle ticket in this particular game. You are losing 95 cents, or you expect to lose 95%. In other words, if we did it over and over and over again, we lose 95%. In other words, someone's going to win, but on average, the loss is 95%. Okay? And the reason each ticket owner will lose, no, they don't, not each ticker, someone's going to win. Someone's going to win $50. All right? Someone wins $50. Okay. So 19 is B. I did not circle that very well, but nonetheless, 19 is B. All right, number 20. Suppose that on a hypothesis test for a single population, HA, the mu is less than 10. So here's what we have. Mu equals 10 would be our null, and our alternative is mu is less than 10. For a fixed sample size and significance level, the power of the test will be greatest if the actual mean is which of the following. Well, let's talk about what our t-statistic looks like. Our t-statistic looks like x bar minus mu over s divided by the square root of n. So they say we're fixing the sample size. And by the way, if you increase n, power goes up. If you increase alpha, power goes up. You need to know that. That wasn't part of this question. They told them they were fixed. But here, they want to know magnitude. As this distance gets further and further apart, so as this distance increases, power goes up as long as it's in the correct direction. So we know we have a mean of 10. What would we need our x bar to be? Well, we need to be less than 10 and as far away as possible. The one that's farthest away and less than 10, because these don't count. All right, these don't count because they're not less than 10. The one that's farthest away and is less than 10 is 8. This will give me my greatest magnitude, and is in the correct direction. Because you could argue 13 minus 10, 8 minus 10 is 2. 13 minus 10 is 3. This has a larger magnitude, but it's not in the alternative hypothesis direction. So it's in the wrong direction. This is in the correct direction of a less than. So, and it has the furthest away. So it has the greatest magnitude in the correct direction. So 20, the answer to 20 is A. I will have more power with an x bar of 8 than I will with an x bar of 9. Likewise, if I had an x bar of 7, I'd have more power. Okay? All right, hopefully that helps with that. Very important to memorize that. And by the way, I would study that question